Alhamdulillah, salatu wassalam ala nabiyyina Muhammadur Rasulullah sallallahu alayhi wasallam. Welcome to the third part of this series where we are going to discuss about the few more IO operations, and this is the second part of this. Uh, in this, we are going to discuss about few fundamental concepts about the input-output operations, along with the relationship between the file descriptors and uh, the file systems. So, to begin with, we will first discuss the one of the very important concept named as atomicity. And atomicity is an assurance that kernel has performed the single system call as one operation without being interrupted. Why it is important is that let's go through the code and we will understand why the atomicity of an operation really matters. Let's say we are seeking an offset of the file after the end of the file. That means the we are seeking an offset, the first byte after an end of the file, and after that we are checking an error check for the lseek command. And let's say this is the process A, and it's checking for a file which is present on a disk. Uh, and during the error check, the process B writes to the file, and the time when we execute it, it goes to the code, the line number 3 on in this program. The process B has already written something on a file, and that thing has caused the offset to be changed. But we have read the offset, which is an old offset, and now the offset of the file is changed. That means whenever we are going to write something onto the file using the old offset, we are going to overwrite the changes made by the process B, and that's not a desirable. And this is how the violation of atomicity takes place. This is generally known as a race condition or time to update or time to seek. The second thing we are going to cover here is a file control operation. The file control operation system call is a system call which we can invoke in order to uh, understand the or to get the current flags associated with the file and to modify them. Now, this is the syntax which we are going to follow for next of our tutorials, where we will first describe the system call name or function name. Then we will describe the type of the function or system call which we are describing, whether it is a function or system call or macros or POSIX definition, whatever. And then we will see a general syntax of that particular system call. Here we get in the file control system call, we need to provide the file descriptor and the commands. The commands are the just uh, an argument provided to this function which tells function to what kind of operation it wants to perform on the file, whether to retrieve the flags or to set the file or set the flags. So in general, we will get the f underscore get fl to get the flag, to get the info of the file, that is the flags which are available on the file or in which mode the file is open, and then the set flag operation. For example, let's say you open the file in a read only mode, and now you want to write to the file in the middle of the program, or maybe the situation arises where you want to write to the file on the particular condition. Then you can set the file file flag to the right or append, and then you can overwrite the file. We will not be going to check the program for this operation or for the system call. Maybe in future videos we will see how we can utilize them. Now the main topic is the relationship between the open files and the file descriptors. To understand the relationship between these uh, two concept or two things, we need to understand the three data structures maintained by a kernel. So all of these data structures are maintained by kernel, and these are the data structures related to the open files and the file descriptors. The number one is the per process file descriptor table. It keeps the information like the flag of the file, or in which mode the file process has opened the file, or process has which kind of access method available to the file, and the pointer to the file descriptor table. So which file, whatever file is open, we have the pointer available in this data structure. And this is a private data structure, so every process has its own data structure per process file descriptor table, and they are unique to we cannot say unique, but they are personal to the process. So the process A might have the file descriptor which are not visible to the process B. And let's move to the second, that is the system wide file table. And the system wide file table maintain the very important information like offset of the files, whether it is modified by the read or uh, by the read, by the write command, or by explicitly modified by the lseek command. It keeps the track of the all files, every files offset. It also keeps tracks to the file access mode records, and in which mode the file is being accessed, and keeps the record to the pointers to the inode table and status flag records. And the third one is inode table, and inode table will keep the records of more generally about the general information about the file. For example, the name of the files and what type of file it is, if it is a general file or socket or pipe or something else. Second thing, it keeps the record of the pointer to the block that holding the file. It's the actual address where your file is residing on your disk. So it holds the record of that particular block, and the metadata of the file, of course, like information like when the file was created, when it was last modified, size of the file, and ownership of the file, that's etc etc. Now let us understand this all these three data structures in the one in this slide, and how they are manifest into the working, and how they are useful to why the kernel is maintaining these three data structures, and how they are useful uh, to in order to achieve the few fundamental concept like atomicity, in order to when we are writing the program. So let's consider the first example. Before the example, let's go through this slide very quickly. We have the two file descriptor tables here. As I said, this file descriptor table here on left side, it's for the process A, and this is the file descriptor table for the process B. All of these elements are private to the process, and they are not shared. Whereas on the contrast, we can see the open file system have the elements which are shared between the multiple files and processes, and there is a reason for it. And here we have on the uh, rightmost side, we have the inode table. Now let's go to the first concept for first demonstration. Now here we can see the process A has the file descriptor 1 and file descriptor 20, pointing to the uh, same open file system, open file table entry. So what it say, what it can interpret is that the file descriptor 1 and file descriptor 2 are pointing to the same open file system is because of the fact that they are might be the duplicates, or they might be the file descriptors are the same descriptors, uh, but they have been duplicated either by using the dupe uh, dupe system call, or a file control system call, fcntl system call. So these three system calls can duplicate the file descriptors, and when they do that, these all the file descriptors which are duplicated, because the fd1 is same as fd20 and it's pointing to the same file. So so this is how this file has we know that these two the tables are pointing to the same file. And in second example, let's say the process A has the file descriptor 2, which is pointing to the 73rd entry of the open file system, open file table, and the process B has the file descriptor 2, which is also pointing to the 73rd of the entry of the open file table, which can be interpreted as the process A and process B are somehow related, and that might be because of the fork. This might be the case where the process A could be the parent process of process B, or vice versa. So in that case, we are tracking the descriptors of the process A and process B, and let's say the parent and child wants to share the same file descriptors, so they will be pointing towards the same file, and they will be sharing the file descriptor. And here in third, we can see the file descriptor 3 is pointing to the 86th entry in the open file table, and process A's file descriptor 0 is pointing to the 0th entry, and they are both pointing towards the same file, that is 1976. Now here one of the that means that this two file these two processes have opened the one file. That file 1976 is being operated by process A and process B simultaneously. The one of the advantage of this architecture is that, let's say, assume the scenario where process A and process B both are trying to write to this file, and let's say process A has taken the taken the file, taken the control of the file and written something on the file, and process B now wants to write to the file. So until the file is under the control of the process A, it should not allow process B to write to the file, and this is how we can uh, we can achieve the atomicity and overcome the problem of race condition. Now once the file is being written by the process A, the process B can continue its operation. But the one thing you might have noticed that the open file table also has the offset of the file. So when the process A has completed its operation of writing the file, it has also updated the file offset of the file. And now whenever the process B is going to write to the file 1976, it will be going to write to the updated offset, and it is not going to overwrite the changes made by the process B. And this is the one of the advantage of this architecture.